Hi, in this video I am showing examples of objects that are moving with a constant velocity. In this case, I've taken a video of me releasing a little battery-operated car along a surface in our lab table. Let me just show the clip first so you can see what's happening. You see, I let go of a car. Well, first I turn it on. I let go of the car and then I release it, and it basically moves across the surface of the table. You can see that I've already taken time to do the video analysis, and I've tagged the position of the car at regular intervals. One of the more important things to see here is that the spacing between these intervals is constant. So between 0 and 1 seconds. Now, by the way, I'll tell you this right up front. Each one of these intervals is 1/3 of a second. So I'm going to end up moving this graph over, or this video over here to the side. You'll see that there's a graph of the x position versus time, which is kind of interesting because it's generated from the video. So let's go ahead and take a look at the graph down here. Take a look at the x-axis on the graph. You can see that I'm at 1 second, and therefore I've got 3 specific dots drawn on here. That means that 1/3, 2/3, 3/3, or 1 second has elapsed. If I then go over here to the graph and move to 2 seconds, you can see, not quite exactly, but I've got 6 dots. So once I go back over here, oops, I need to plant it right here, and then you can see that I've got 6 dots. 1, 2, 3, 4, 5, 6. So every one of these dots that I've drawn has occurred at 1/3 of a second. That's the interval. It's important to recognize that the spacing between these intervals is the same, and that's true for an object that's exhibiting uniform motion, or the characteristics of uniform motion, or another way of saying that is its velocity is constant. You can also see that the function that's generated by plotting the position versus time is linear, and I can do some other things with this if I want to. I can basically grab some of these points, the more the better, and I can do a linear fit, and it's going to, the little regression tool here is going to tell me I've got a very, very strong correlation. You can actually see that almost all of the points from my collected video analysis are on the line, and as I hover over here and move this, watch what happens to the car on the left-hand side of your screen while it's moving across. Okay, so what does this all mean? It means that objects that are moving uniformly or with constant velocity generate linear functions when position versus time graph is plotted. You also should know that the spacing between these intervals should be the same. So from this dot to this dot, that distance that occurred in 1/3 of a second is the same distance that the car covers in the next second. So this distance between those two dots is the same. Now, what's important about this to know is a couple of things. One, I can say that v bar, or my average velocity, is simply my change in x over my change in t, or my time interval. This, by definition, is what average velocity is, or another form of this that you might have seen before is velocity is equal to distance over time. You can write this simply in this format when an object's motion is uniform. Technically speaking, though, this is the better definition because it describes the average velocity. If you were to remember from your math classes the slope of a line, and there are a bunch of different ways to write this, but we can write it as the rise over the run, or the change in y over the change in x. So again, I'll go ahead and write that out since there's a lot of different ways that people remember this. But the rise over the run, take a look at this graph over here on the left. I'm going to shut this little examine tool off. Take a look at this. So I'm going to go up a certain amount, that's my rise, and my run is how much I go over. And then I can do that again for the next line, the next 2 data points, my rise over my run. And so I should be able to recognize that the rise in this particular case is my change in x, and the run is my time interval. So that makes a lot of sense. When I go back here to what I've written, the slope of the line is the rise of the run, or more technically, my change in x over my change in t. Take a look at that and that. So the slope of a position versus time graph, the slope of the function, is the velocity.